Okay, we will go through the exemplar problems in the class 11 physics, chapter 7, system of particles and rotational motion. Okay, now how to find the direction of the angular momentum and angular velocity using the right hand thumb rule. Okay, so you curl your fingers in the direction of the rotation, then thumb gives the direction of the angular momentum as well as angular velocity. This is for the symmetrical system. Okay, so you can also find the direction of the torque and angular momentum using this animation. Okay, there's different colors they are given, so you can find the direction of the torque, how this torque direction changes. Okay, so in this. Okay, now see, there is a angular velocity and linear velocity. Suppose you take this disk, okay, and let us say 2 points, this A and B. B is here, A is here. So the angular velocity will be same for both the points. Okay, for this point and this point, they take same time to make the one rotation. Okay, so that means angular velocity will be same, but the linear velocity will be different because this circle has the more distance than this circle. So this but the distance is covered at the same time. Okay, this distance is covered at time with let us say 1 second, means this distance also covered in 1 second only distance varies. Okay, that means within 1 second this point covers the more distant than this point. That means velocity of this point, linear velocity of this point is more than this point because they cover the distance at the same time, but distance is this point covers the smaller distance, this point covers the more distance. Okay, linear velocity here will be more than the linear velocity here, but the angular velocity is same. So the relation between the linear velocity and angular velocity is this. Okay, so this velocity will be greater than this velocity. So linear velocity equal to angular velocity into radius. So here radius is more, so that means this velocity is more, that is linear velocity, than this. Here radius is less. Okay, that is the angular velocity and linear velocity. Okay, this angular momentum for a point, okay, for with respect to a point, that is important, is position vector cross linear momentum. Okay, so this is for L equal to moment of inertia into angular velocity. This is for the extended object. Okay, this is for the point object, this is for the extended object. So angular velocity equal to change in the theta divided by the time. Okay, from here to here how much angle is covered within this time. Okay, that is the angular velocity. Okay. So this is the direction of the angular velocity in clockwise and anti-clockwise. Anti-clockwise positive key, clockwise negative key. Okay, linear momentum equal to mass into linear velocity. Both are in the same direction. Okay. But the direction of the angular velocity and angular momentum need not be same. Can be same or need not be same. Okay. So when you say circle and this distance is called arc length along the circumference. If you cover from here to here, this distance is called the arc length. Okay, the tangential velocity equal to arc length divided by the time. Okay, this arc length. The angular velocity is change in the angle divided by the time. Okay, so torque equal to position vector into the force, and that angle of the direction of the torque also we can find using right hand thumb rule. I already showed you. So period is nothing but the time taken to make one rotation, that is the period. 1 divided by period is the frequency. Okay. Now, what is the perpendicular axis theorem? Okay, if you take a plane like this and the z axis is perpendicular to the plane, we have x and y axis that is on the plane. Okay. So this moment of inertia of the z-axis is equal to the sum of the moment of inertia of the x and y-axis. Okay, these are the conditions. Z should be perpendicular to this plane and x and y would be on the plane, perpendicular to each other. This is for the 2D only. Okay, two-dimensional systems only. Okay, they have the common point. This x, y, z, they have the common point. Okay, these are the conditions for this perpendicular axis theorem. One more thing, the general information, we want to find the mass of some system, that is equal to density into the area for the two-dimensional object. Density into area will give the mass of the two-dimensional object. So we have a parallel axis theorem also. Okay, parallel axis theorem. So if you take a axis, the one axis here, one axis here, this to apply this theorem, these two axes should be parallel to each other. Okay, here this axis and this axis, this should be symmetrical. And these we should have the moment of inertia of the center of mass. Okay, this is the center of mass, so we should know the moment of inertia through the center of mass axis. Okay, we should know these two axes should be in parallel and this should be symmetrical. Okay, these are the conditions. When it is satisfied, we can use the parallel axis theorem. So the moment of inertia of this axis equal to moment of inertia of the center of this axis plus ma square. M is the mass of the whole system. A is the distance, perpendicular distance from the center to this axis. Okay, moments of the system. A is the distance between this axis and this. So if you take example, for this system is 2 kg 2 kg 2 meter from the center, and this is the moment of inertia. Okay, here 16 kg meter square is the moment of inertia. To find out the moment of inertia about this axis using this theorem, parallel axis theorem. Okay, we find using the theorem I dash equal to ICM, this is this, plus MA square. Your total mass is 4. Okay, 2 plus 2, 4 total mass, and the distance is 2, so this is 32. Okay, from here to here the distance is 32. This is using the parallel axis theorem. You can also find out using the normal thing. Okay, for this axis, okay, for this mass distance is 0 and this mass distance is 4 from this mr square, if you use this formula. Okay, so here the first distance is 0 from that mass for that axis. So okay, here too this distance is 4 square 16, so 32. So this also, so same thing is coming. So using the parallel axis theorem, and normally also you compute the same thing will come. Okay, find which of the following does the center of mass lies outside the body, so pencil inside the body, disc inside the body, this bangle, okay, bangle, the center of mass lies outside the body, that is outside the body, inside that bangle ring it is. Which of the following points is likely the position of the center of this system? Okay, here the both are equal volume, but the volume of the weight of the air will be less than the weight of the sand will have the more weight for the equal volume. Okay, so this will have the more weight than this, so to balance the weight this point will move slightly towards that sand. Okay, not here, this is one sided, so here slightly to balance the this other side of the weight and this weight. A particle mass of m is moving in the yz plane, uniform velocity, and its trajectory running parallel to the positive axis, intersecting. Okay, the change in angular momentum. The change in angular momentum about the origin. Okay, about the origin. Change in angular momentum. They are asking. Okay. Bounces electrically. Okay. So the velocity is v, direction is y, ey, initial velocity. Then after bouncing back, it will be the same velocity but in the negative direction. Okay, minus y. The angular momentum about that point L is r cross p. Okay, position vector into the linear momentum. Position vector. Okay, this position vector is represented by both these dimensions, y and z dimensions. Okay, this is a constant. Okay, a z and some constant into this y position vector. L equal to r position vector and to linear momentum. Linear momentum the final minus initial. Okay, final, this is the final velocity minus ey minus initial velocity, and this one is the position vector. So after multiplication, the important thing is here this if you cross product of the same vector y into y will be 0, so z into y will be minus x here. Okay, when you do e cross ey it will be minus ex, so this is minus ex. Okay, this into this will be 0. Okay, y into y cross y, this will be 0. Okay, only this term will be remaining. Then after simplification you will get this. So this is important here. When a disk rotates in the uniform angular velocity, okay, velocity uniform, that means acceleration will be 0. So which of the following is not true? Okay, they are asking which is not true. Okay, the sense of the rotation remains the same, that is true. The orientation axis of the rotation, that is true. Speed of the rotation, okay, that is true. But angular acceleration is non-zero. This is not true. Angular acceleration should be 0 because of the uniform velocity. Okay, this is not true. A uniform square plate has a small face Q of a irregular shape removed and glued at the center of the plate. Center of the plate. This is removed and here at the center of the plate. Shown here the moment of inertia about the z-axis. This is they are asking. Actually, when you move some mass toward the center, that moment of inertia will decrease. Okay, because of that moment of inertia will have a parameter distance that decreases. Okay, so and this new moment of inertia will move in the axis of the line connecting this point to the center of the axis. Okay, so it will move in this. so it will decrease, center of the decreases. The new center of mass of the following quadrant. Okay, the opposite, it will move in this direction, where the line join the center of mass, and it will be opposite to this, so it will be in the third quadrant. So it will move, the center of mass mu will, like, so it will be somewhere here in the third quadrant. Direction of the q, direction of the center of mass movement opposite to q joining the axis of the rotation. Okay, the density of the non-uniform rod density function is given. Okay, uniform length is given, where a and b are the constant. The center of mass. Okay, we have to find the center of mass. So this is the set density function. So we differentiate with respect to the distance. Okay, so dm and dx. Okay, see, after differentiation, after this thing, integrate over the distance, so you will get this finally. Okay, 0 to 1, so you can go through it. Here you go around. Okay, made a ring-like platform radius r, and the mass m is revolving the angular speed. They are given the angular speed. A person of mass m is standing on it. At one instant, the person jumps off the round radially away from the center around. Okay, the speed of the round after this is they are asking. Okay, this is based on the law of conservation of the angular momentum. Moment of inertia, the angular velocity, angular momentum, conservation of the angular momentum. So this is the initial thing. Okay, for the platform and the person, that is the moment of inertia in the angular velocity. Then after jumps off, okay, this is the person is not there, only for the platform angular momentum, so these two are equal. So the after simplification, we will get the angular velocity equal to 2w of the initial velocity. Okay, final angular velocity is the 2 times the angular velocity, the initial angular velocity. Choose the correct alternative. Okay, for a general rotational motion, angular momentum L and the angular one need not be parallel. Okay, it need not be parallel. General. So in some cases where it need not be parallel, if the axis of rotation is moving, and also it is not a symmetrical system, so that time it will not be need not be parallel. This omega and L need not be parallel for a rotational motion. Okay, for a rotational motion, the angular momentum always this is wrong. Okay, need not be parallel is correct. For this is for the translation motion, the momentum p and the velocity always this is correct. This is for the translational motion. Okay, See here this angular momentum and angular velocity need not necessarily parallel. But for the translation, the P and V are always parallel. Okay, this is for the translational motion, this is for the rotational motion. Rotation need not be parallel, but for the translational motion it is parallel. Figure 7.5 shows the particle 1 and 2 each of mass m moving in the opposite direction at the same speed, the parallel lines. At a particular instant, R1 R2 with respect to the position vectors they are given from the point A. The parallel axis is the correct option. Okay. Angular momentum. Okay, this is angular momentum with for this position vector r1 with respect to this point is this. Okay, so remember you have to find the direction of this using the RHS rule. Okay, right hand thumb rule. So here dot, that is going into the plane, and L2 is going come this out of the plane. One is into the plane and out of the plane. And then we have this. If we change the sign, then it will become, both will become in the same direction. Okay, so we are changing the time. Okay, sorry, we are changing the sign. Okay, if you put cross here, then dot will be instead of dot, then it will be negative sign opposite to that. So you will get the final angular momentum. Okay, this option is correct. So there are two options which are correct. Okay, this is correct and this is correct, not this. Okay, question number 11. The net external torque on the system of particle about an axis is 0. There is no external torque acting on the system of particle. Which of the following is compatible with it? Okay, the forces may be acting radially from the point on the axis. So radially means it will be, the angle will be 0 between R and F. So torque is the cross product of the position vector in the force. The radially from a point on the axis means that the angle will be 0. Different, so sine 0 is 0. So okay, the forces may be acting axis of the rotation. So here will be position vector will be 0, and the force and the axis of the rotation is same, then the position vector r will be 0 distance. The forces may be acting parallel to the axis of rotation. Okay, so in this case there will be some torque, but that is out of the plane, not in the plane. Torque won't be there on the plane. Okay, the torque caused by the some forces may be equal and opposite to that of the caused by the, this may can be, so all the points are true. Okay, figure 7.1 show the luminous xy plane. The axis z dash are perpendicular to its plane. A force F acts on the lamina. Okay, this is closer to this axis. Okay, here if you use RHS rule, you have to be careful. See the R points, the index finger is the R here. Okay, so use the index finger for the position vector for the RHS rule. Okay, so the torque, so if you apply rules, the direction is this is not true. Okay, here it is minus k is given, then that is not true. This is true, the direction k final torque position for this is direction k. This is true. Torque T caused by the F on the z-axis is greater than the magnitude because they are given point this P is closer to this axis. That means distance from the z-axis more. So that is why the magnitude is more in this. Torque of magnitude of the torque is more. More distance, more torque, because r cross the distance r more means more torque. The total torque is given by these two. This is not true because they are at this different axis. Okay, not you cannot add like this. Okay, their torque is in different axis. With reference to this, okay, whether the following is true or false. The moment of inertia about the cube about the z-axis is this. So as I already told you, this theorem is not applicable for this 3D object. It is only for the 2D. Perpendicular axis here is only for not applicable for 3D. So this is false. The moment of inertia about the cube about the z-axis, okay, the distance from the z-axis is a divided square root 2. Okay, a divided square root 2. So when you square this a divided square root, then it will become a square by 2. Okay, new moment of inertia equal to the moment of inertia through the center plus ma square is the formula. So here is a by root 2, so a square by 2. Okay, so you can go through this theorem. The moment of inertia of body about an axis equal to sum of the moment of inertia. Okay, this is that formula. The here a is a by root 2 there. Okay, and e square. Moment of inertia of the okay, because that is not parallel. Okay, this axis is not parallel, so you cannot apply this rule here. By symmetry, this is true. Okay, center of gravity of the body of the earth consider the center of gravity of the external object not. What is the quantitative meaning of the small and external object in this regard? Okay, see, when the vertical height of the object is very small as compared to the earth radius. Okay, vertical height of the object is very small as compared to the earth radius, we call it small, otherwise it is extended. Okay, so this is important. Why does a solid sphere has a smaller moment of inertia than the hollow cylinder? Okay, this is very important. Hollow cylinder is less weight than the solid sphere, but still the moment of inertia of the solid sphere is less than the hollow cylinder of the same mass and radius. Same mass and radius. Okay, here important, same mass and radius about an axis passing through the axis of the symmetry. Okay, this is the moment of inertia formula. All the mass in a cylinder lies on the distance r, that is more distance. Hollow cylinder, the mass lies on the outer ring from the axis of symmetry, but for the solid sphere it lies at the smaller distance. This r will be smaller, so when you sum m r square, then the moment of inertia of the solid sphere will be less than the moment of inertia of the cylinder. That is important. The variation of the angular position theta of a point rotating rigid body with the time is given. Okay, so here the theta is increasing steadily from negative to positive. The body rotating in the clockwise and anti-clockwise. Theta increasing means anti-clockwise. Okay, anti-clockwise. Positive slope indicates anti-clockwise direction, which is traditionally taken as positive. So when a uniform cube of mass m and side A is placed on a frictionless horizontal surface, a vertical force is applied at the edge. Okay, force is applied. So you can go through the book for this formula. Okay, cube will at this condition cube will not exhibit motion when the force is greater than this. Then the cube will begin to rotate and slip at A. Force greater than mg, cube will move up. Mg is the gravitational force. When you apply more than the gravitational force, this will move up. So you can go through this thing. A uniform sphere of mass and radius is passing through the horizontal surface. The sphere is struck horizontally at a height h from the floor. At h, okay. Which of the following? Match the following, okay. So under this condition, when this height equal to this r by 2, then this will take place. So you can go through these conditions. A vector sum of the system of non-collinear forces acting on the rigid body is given as non-zero. The vector sum of the all torques due to the system of forces about a certain point is found to be zero. Does that mean it is necessary zero about any arbitrary point? No, that is not true. 7.19. Okay, this is given the sum of the torques about a certain point is given. Sum of any other point, that is need not be true. So, okay, this may not be zero. Okay, need not vanish. A wheel is the uniform motion about the axis passing through its center perpendicularly considered to be in the mechanical, translational plus rotational equilibrium because no net external force or torque is required to sustain its motion. However, the particle that constitutes the wheel experiences centrifugal acceleration directed towards its center. How do you reconcile this fact the wheel is being in equilibrium? Okay. The centrifugal acceleration to a wheel arises due to the internal elastic forces which pairs cancel each other. Being the symmetrical system, these forces will cancel out each other. Okay, but in a half wheel, the distribution of mass about the center of the axis of rotation is not symmetrical. Okay, so therefore the direction of the angular momentum does not coincide with the direction of the angular velocity. I already showed you the angular momentum direction, angular velocity direction will be same only for the symmetrical system, not for this unsymmetrical. So here this is important. The direction of the angular momentum does not coincide with the direction of the angular velocity here for the half wheel because that is not symmetrical, and hence the external torque is required to maintain the rotation. A door is hinged like this, okay, at the one end and free to rotate the vertical axis. Does the weight cause any torque about the it will not cause because this force is parallel to the axis of the rotation. Okay, that will not cause any torque. Okay, gravity is parallel to the axis of the rotation, so it will torque will be away from the plane. It will not affect this rotation. it will know. No, the force can produce a torque only along the direction normal to itself. So when the door is in the xy plane, the torque produced by the gravity can only be along z and minus z direction, never about an axis passing through the y direction. N minus 1 equal point masses of each of mass m placed at the vertices of the regular polygon. The vacant vectors, that is n. N as a position vector. Position they are given on the last point with respect to the center of the polygon. That is important. Find the position vector of the center of mass. Okay, so if you divide this into two parts, one is n minus 1 particle and another nth particle. So this position vector of the nth given, they are given as a, okay, equal mass, all are having equal. The n minus 1 particle, you assume the position vector as a b, n minus 1 into this mass of this many particle into b plus this is the last one divided by the total mass, that is all masses are same. Okay, because they are given with respect to the center of the polygon, that is origin. So that is this will be 0, that means center of position vector is center of, because it is with respect to the center of the polygon, so then it is 0. So if you equate this and you will get this position vector will be minus a by 2 n minus 1. Find the center of this half disk and the quarter disk. Okay, half disk and quarter disk. 23. So the density of the disk, okay, density into area will give the mass. Okay, so for the half disk they are integrating from 0 to pi. For the symmetrical system, that is 0. Okay, the center of mass will be with respect to x 0 for the symmetrical system. Okay, for the quarter disk they are integrating from 0 to 5 by 2. 0 to 5 by 2. So the axis is symmetrical about the x-axis, so this will be 0. Then for the center of mass y-axis is this. So the total center will be 0 comma this 4a by this. For the quarter disk we have to integrate from 0 to 5 by 2. Two disks of moment of inertia I1 I2 affect their respective axis normal to the and the rotating the angular speed is given and brought in contact with the axis of the rotation. Does the law of conservation of the angular momentum applied in this situation? Yes, you can apply the law of conservation of the momentum because there is no net external torque on the system. External forces, gravitational or normal to the normal reaction act through the axis of the rotation. So they are acting parallel. So hence they produce no torque on the system. Okay. So this is now the new angular speed of the total system after in contact. Okay, I equal to I1 plus I2. Calculate the loss in kinetic energy due to the friction. So this is combined moment of this combined angular velocity from this. You are substituting here. So this is the kinetic energy. It is like half mv square. M is nothing but the moment of inertia here for the rotational motion. V, instead of v, we are using angular velocity here. Account for this loss. The loss in kinetic energy is due to the work against the friction between the two. A disk of radius r is rotating with the angular speed about the horizontal is placed in the horizontal table. The coefficient of the kinetic friction. What was the velocity of the center of mass before being brought with table? So the velocity will be 0 before being contact with the table. Okay, pure rotational motion. The velocity of the center of mass is 0. Pure rotational motion. What happens to the linear velocity of a point on its rim when it's placed in contact with the table? The linear velocity on the rim will decrease because due to the friction. What happens to the linear speed of the center of mass when contact with the table? So now due to the friction, the center of mass will acquire some velocity. So this will decrease, but center of mass will acquire some velocity, so it will increase. Which force is responsible for the effect of B and C? Okay, that is the frictional, due to the friction. What condition should be satisfied so rolling to begin? Okay, velocity of the center of mass is the angular speed into the radius. When these two equal, then the rolling will begin. Calculate the time taken. Okay, this is how they are computing the time. Okay, this is the condition for the rolling to start. Okay, you can go through this answer. Two cylindrical hollow drums of radius r and 2r of same height, common height, are rotating the angular velocities clockwise. One is rotating clockwise, other is rotating in the anti-clockwise. Okay, anti-clockwise, and small drum is anti-clockwise and the big drum is in the clockwise direction. Their axis pictured in the parallel horizontal. Okay, with some distance delta. They are brought in contact, that is delta is 0. Now they are brought in contact. So the frictional forces just after the contact. So friction is against the direction of the rotation. The small drum is rotating the anti-clockwise. Okay, the friction will be the opposite for the left drum. Force on the left drum, that is smaller drum, will be upward. The force on the right is downward. This is the direction of the angular velocity of this is the anti-clockwise and this is the clockwise. The friction is against the rotation. Identify forces and torque in the external system just after contact. What would be the ratio of the final angular velocity when the friction ceases? Okay, final angular velocity, that is the combined angular velocity. So the external torque is the anti-clockwise. This direction they given the anti-clockwise direction. This is the final torque. So this will be the when finally there will be when there is no friction, then this will velocity will become the this. linear velocity. A uniform square and the uniform rectangular plate are have the identical. This is area is same on the both the object, and mass and area are the same. Okay, so show that they prove these conditions. Okay, so here the moment of inertia about the x-axis of this rectangular is less than this, because when you say x-axis, this axis, the distance from the x-axis is less here in this rectangle than here. So you say x-axis, we have to consider this distance, that is the about x-axis. So this rectangle moment of inertia about the x-axis is less than this because the distance is less here, distance is more here. So using this rule, this B is less than this C. Using these rules, we can prove this condition, and this you have to use the perpendicular axis theorem. Perpendicular z equal to x plus y. You have to use that. So you can go through this. Both are same area, same mass. So this we have to use the perpendicular axis theorem. A uniform disk of radius is resting on the table of the wing. The coefficient of the friction between the disk and the table. Now the disk is full with the force F. What is the maximum force for which the disk rolls without slipping? Okay. Okay, this angular acceleration I alpha, force into radius equal to moment of inertia into the angular acceleration. Moment of inertia, if we substitute, then force, will get this formula, small f, that is the friction. So this force minus the friction is the m, the acceleration of the center of mass. The acceleration of the center of mass is given to for the rolling to start. So then you substitute this m by 2, the r alpha. R alpha, for this R alpha you substitute this, okay, because the acceleration center of mass is R alpha, so you substitute this, then you will get this force equal to 3 mu mg. Okay, so force, then this is the condition. Okay.